This is going to look at some very quick examples of calculations for strong acid versus weak acid equilibrium systems. The short of it is this: strong acid equilibrium systems, or strong electrolyte equilibrium systems in general, have very easy calculations. All right? And weak acid or weak base or weak electrolyte equilibrium systems have more work for the calculations. In fact, you will almost always do what we call ice problems, and that relates to some of the equilibrium stuff we've looked at before. So I'm going to leave those there, and I'm going to try and color code this as we go. A couple things that I want to address before we get going. We're going to assume for these calculations that the temperature is 25 degrees Celsius, so we can use our K value of 10 to the minus 14th. And then I want to throw in this vocabulary term of percent dissociation or percent ionization. Right? Or percent ionization. That's just a ratio of the dissociated amount or the ionized amount to the initial amount at equilibrium. All right, and I guess we can just say 2 there. So our equation for percent dissociation is going to be X, which is going to be our change amount in these ice problems, over the initial concentration. So our notation there, open brackets is concentration, little subscript 0 is like carryover from physics and everything else, initial because time t equals 0, so that's our notation for initial concentration, and that's times 100. All right, that's how we get percent dissociation. I'll leave that over there. This is a way that we can compare strong and weak. Strong acids are going to have 100% dissociation, strong electrolytes. Weak acids, weak electrolytes, are going to have less than 100% dissociation because strong electrolytes dissociate completely and weak electrolytes don't dissociate completely, qualitatively speaking. So the type of problem, let's like write out a question that we could ask here. So we're going to be given something. I want you to calculate some stuff. All right, so given some acid concentration, 0.250 molar HCl in this case, find whatever, like, we'll find the same, I don't want to write it again, but I will, find the concentration of all species at equilibrium. We could find the pH and the pOH or whatever. Let's just find the pH, and let's get the percent dissociation. And I'm going to do this the long way, and then I'm going to mention maybe over here that we didn't have to do it the long way. HCl, we have a K value for that. It's large, and I literally do mean large. Whenever you see these equilibrium system problems of any type, and I tell my students this all the time, write the equilibrium equation, write the Ka expression, set up this ice problem, and I'll write it kind of big over here so that if it's the first time you've seen it, it's pretty clear. So we've got HCl and H2O, and we did a lot of practicing with this, writing aqueous dissociation equations and coming up with K expressions. Sorry, I'm debating if I can fit this in here. Ka, H3O plus, Cl minus, over HCl. And that value happens to be large. All right? Therefore, HCl is strong. I realize that's a mess at that point, but you can stare at it and interpret it. So that is our aqueous dissociation equation. That's our K expression. I know it's strong because the Ka value is large, literally the word large from a table of K values. So that's not something ambiguous. It says large because the number is big. When we do an ice problem, and this is a super common thing in chemistry, what we're really saying is that we have some initial amount. That amount is going to change, and we are going to reach some equilibrium. and then we do some math to make it happen, and that math involves this. So the reason I tell everybody to set these up for any equilibrium system is like, here's a bunch of words, I need a place to put the numbers in there from a word problem, and this lays out a template where we can put all our words. So for instance, we have a 0.250 molar HCl solution. Well, that means my initial concentration of HCl is 0.250 molar. Water is a pure substance, so I'm not worried about its initial concentration. I haven't made any chloride yet, so it'll be 0 molar, and that leaves the H3O plus. But let's rewind the tape a bit. 0.250 given. Pure substance doesn't matter. Haven't made any yet, 0 molar, but then there's water. And if you look back a couple videos, water auto-ionizes, and at 25 degrees Celsius when it auto-ionizes, it is still neutral, but it is neutral with a concentration of 10 to the minus 7th for the H3O plus, and 10 to the minus 7th for the OH minus. So this is 10 to the minus 7th molar. And I'm going to put that in parentheses because rarely does it come into play. But it's there and it's true. And I'll say it again in slow-mo. Before HCl is dissociated, water was like this. And I hadn't made any chloride yet. Water did this to itself. Now things are going to change. And the amount they're going to change is all of it. Okay? So this 0.250 is going to go down by 0.250. Because strong electrolytes dissociate completely. This is changing completely, and we'll end up with 0 molar. And I'm going to put that in quotes because there's no zeros in equilibrium systems. But for practical purposes, it's pretty darn close to 0. In this particular case, we'll have to go up by 0.250, and we'll have to go up by 0.250. And we are following our stoichiometry rules. It was a 1-to-1-to-1 ratio. My dog's puking in the background. We end up with 0.250 molar and 0.250 molar. So at equilibrium, this is gone, 0 molar. At equilibrium, the H3O plus is 0.250 molar, and at equilibrium, the chloride ion concentration is 0.250 molar. Super easy. Remember when I said that? Well, there it is. So let's write out the answers I asked for, and let's just mention, maybe with a second example, how we could have saved some time with that. So, concentration of species at equilibrium. So at equilibrium, what do I have? Well, I have HCl, which is kind of a lie, but kind of not. And that equilibrium concentration is 0 molar. And again, that's not really a 0. And so, like, when you look at answer keys for books or tests or whatever, generally they won't include the strong electrolyte or the strong acid because it dissociated completely. But I like to see it there because it's saying, well, this is what we started with, and it's kind of all gone, even if it's not technically all gone. We have a concentration of H3O plus to worry about. And in this case, that concentration is everything we started with, 0.250 molar H3O plus. We have a concentration of Cl minus to worry about. And again, I'm just pulling these off of our equilibrium row. HCl, H3O plus, Cl minus at equilibrium. Those are my numbers. It's supposed to be 0.250 molar Cl minus. And here's the part where people tend to forget an important detail. When you look at all these equilibrium problems, if you have H3O plus, you always have OH minus. If you have OH minus, you always have H3O plus, because Kw is not 0, so neither of those can be 0. So something I want to watch out for is to make sure that I always include a concentration OH minus. Even if it's not a significant concentration, it's there. All right? We're not lying, and it doesn't take us that long to get it. I'm going to rearrange this equation, and we'll have concentration OH minus as Kw over concentration H3O plus. In this case, that's 10 to the minus 14th over 0.250 molar. And I think that ends up 7.7 times 10 to the minus 13th. And that is our concentration of hydroxide ions. So we have this information right here. That takes care of this, yeah? We'll call that part A or something, right? So there we have our answer to part A. Part B is asking us for a pH, and we could just as easily get a pOH. To get the pH, it's the negative log of our concentration of H3O plus. So pH is the negative log, concentration H3O plus. And in this case, that's the negative log of 0.250. which is going to give us a 0.602 for our pH. As I was writing there, I had a mental lapse, and I had to stop and double check. 10 to the minus 14th over 0.250 is just 4 times 10 to the minus 14th. This number is, spoiler alert for my later example, this should have been 4 times 10 to the minus 14. Alright, sorry for that, but again, had I paid attention, 0.250 is a quarter. 10 to the minus 14th divided by a quarter is 4 times 10 to the minus 14th. Sorry about that. All right, we have our pH, 0.602. We needed to get a percent dissociation. We have that equation up there. Percent dissociation is supposed to be X over our initial concentration. And our change is going to be listed as X from here out times 100. All right, so our X was 0.250, yeah? And our initial concentration was 0.250 times 100 gives us 100% dissociation. Now, why does that make sense? It makes sense because HCl is strong and we expect it to dissociate completely. We expect a 100% dissociation. Let me just label some stuff here. We said that was going to be A, pH can be B, and our percent dissociation can be C, so there's our B and our C. I try to emphasize that when you're looking at work, and I realize it looks kind of like a mess now, but when you're looking at work, it's important that things are labeled and circled or whatever, so it doesn't become Where's Waldo on the page. There's all kinds of stuff going on, but here's the important stuff. That's B, that's C, and that's A. So we've answered that one. So keynote here, we didn't need to do any of that. We could have just done most of it in our heads. And so we'll look at, so that was maybe example 1. Example 2 we'll look at, and we'll just do another strong one. And we'll say given maybe 0.100 molar HNO3 aqueous. All right, I cheated putting that aqueous there because I was sloppy in my writing. We're going to ask for that same stuff, that A, that B, and that C. And I'm going to skip the whole ice setup and everything else. I know it's strong. In fact, maybe I should take note of that right here. Ka is large. All right? Rather important bit of information. If Ka is large, this is strong. And what do strong things do? They dissociate completely. And then our answer to part C is going to have to be 100% dissociation by that reasoning right there. We don't have an answer to B or A, but we can get them very, 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 very quickly. If we have this complete dissociation, our HNO3 0.100 molar is going to give me 0.100 molar H plus, and that's the same as 0.100 molar H3O plus. If it's aqueous, it's in water, the H pluses will stick to waters and make the hydronium ion, and it'll give me 0.100 molar NO3 minus, which I don't care about because that's not part of our acid or base solution. We can now get our pH, and we can get the concentration of everything we have at the final solution. I guess I do care about that right now. So in our final solution at equilibrium, we have to worry about some concentration HNO3. It dissociated completely, so that's 0 molar HNO3. We've got to worry about some concentration of H3O plus, which is what the HNO3 used to be, 0.100 molar H3O plus. We have some concentration of NO3 minus, which was 0.100 molar NO3 minus, because this dissociated completely, and you'll see me write those, I guess, when I write strong electrolyte dissociations. And we still need to get some concentration OH minus, and I'm going to put that in a different color just so it jumps out a little bit that it's taking place. And that's going to be Kw over our concentration H3O+. Let me make sure this is still on the screen. It's good enough. So we're going to have, again, at 25 degrees Celsius, 10 to the minus 14th for Kw over our 0.100 molar for the H3O+. And that's going to give us like 1.0 times 10 to the minus 13 molar OH minus. So we've got corresponding that information there. We've got our percent dissociation. And the only thing we have left to calculate is that pH. And so pH is the negative log of our concentration H3O+, which is the negative log of 0.1. The log of 0.1 is 1, negative 1, and negative 1 is 1, so our pH has to be 1. In terms of sig figs, there is a rule about sig figs. I'm not going to write it right now, but for pHs and concentrations, the number of sig figs in the concentration is equal to the number of decimal places in the pH. So my concentration was actually 100, so my pH, I have 3 sig figs, so I should have 3 decimal places in my pH. Alright, I'm not going to worry about that for right now. That's our part C. Sorry, our part B. That's our part C. And this right here is part A. My dog is back to making noise. Alright, so once again, we didn't need to do ice there, but we're going to for the next example, but answer here, and answer here, and we get all that stuff. We're going to squeeze this last example on the rest of the page, and I think we can handle it. How do things change when we have a weak acid, right? So our third example here, instead of doing HCl, let's maybe do HF. And we'll go with this same number here, 0.250 molar HF. We're going to do the exact same setup. I'm going to be looking for that part A, that part B, and that part C. And I said we need to start out with an aqueous dissociation equation. Any equilibrium system, do this. Set up your K. Get a K value, set up ice. All right. In this particular case, then, we've got HF in water. That's going to give us our H3O plus and F minus, our conjugate acid and our conjugate base. Our Ka expression here is H3O plus. That looks familiar. F minus, that was Cl minus there, but that looks familiar. And a concentration of HF. All right. This has a number, and I got that number from a table of K values. And that number is 7.2 times 10 to the minus 4th. All right? This is tremendously significant because that says to us this is a weak acid. HF is a weak acid. There's a totally different video that talks about why it's a weak acid. But for right now, this is a weak acid. Right? And we know that because Ka is not large. And one more time I'll say it, literally the word large. It is not large. Let's continue setting up this ice problem. Initial concentrations, change in concentration or change in amount, and then our equilibrium amounts. We're given 0.250 molar right there. Water is a pure substance, it's our solvent. Fluoride ions have not been made yet. And water autoionizes. Before this HF dissociates, water autoionizes and gives itself a 10 to the minus 7th molar. The most common question I get is like, well, how do we know if that number matters? Well, up here, what's 10 to the minus 7th, 0.0000001 plus 0.250? It's 0.2500001. That's 0.250. So what I say is, when you have this change taking place, if the value you get there is close to 10 to the minus 7th, go back and recalculate it. So as we look at this, my change is not going to be all of it. So up here, it was strong, and the change was all of it. Down here, it is weak, and the change is not going to be all of it. I don't know what it is. I'm going to lose some amount I don't know. And then this is going to go up by that same amount, and this will go up by that same amount. And it might be worth noting right here, it's not all of it. We don't know how much because it is weak. All right, I'm looking for an appropriate color for that. We can say right here, it's not our 0.250 because the weak acid doesn't dissociate completely. All right, so let's take this change here. I don't know how much is that's going to be, and I'll figure it out up there. 0.250 minus x is 0.250 minus x, literally. 10 to the minus 7th plus x is going to be is going to be x plus a tiny number. That tiny number is probably not going to be important to us, but we can't lie and say it's not there. And this will just end up 0 plus x, which is x. This is a math problem, all right? And that is scary to many people, but we can handle it. If you look, our equilibrium concentration of HF is 0.250 minus x. So this number right here is going to go right there in our equation. The equilibrium concentration of H3O plus is x, and that's going to go right there. And the equilibrium concentration of F minus is x, and that's going to go right there. So we have one variable, x, in one equation, and by linear algebra, we can solve that. And I'll try and keep this logical in the way I set it up. Our Ka value is going to be our H3O plus, F minus over HF, which is those numbers, x times x over 0.250 minus x, which is 7.2 times 10 to the minus 4th. If you're paying attention at all, that's what we call a quadratic. We can solve it in a calculator, like if you've got a TI calculator, you can use something like Solver and just plug it in. In this particular case, when you solve it, x ends up 1.3 times 10 to the minus 2. Okay, and that's 0.013 molar. We now have some answers, right? Our concentration HF was supposed to be 0.250 minus x, so at equilibrium, our concentration of HF has gone down a bit, but not all of it, and we end up with 0.237 molar HF, all right? Our concentration of H3O plus, that, by the way, was 0.250 minus x. Our concentration of H3O plus is supposed to be x, which is 1.3 times 10 to the minus 2 molar H3O plus. And I want to point out, by the way, 10 to the minus 7th plus 0.013. Well, that's 0.013 plus 0.000001, which is 0.013 for all practical purposes. Our concentration of F minus is supposed to be x, which is 1.3 times 10 to the minus 2 molar F minus, and we still have to worry about that hydroxide ion. Anytime you have H3O plus, you also must have OH minus. In this case, that's going to be Kw over H3O plus, as we solved from that Kw expression right there. 10 to the minus 14th over our H3O plus, which is 0.013. We end up with, in this case, the number that I incorrectly wrote over there, 7.7 times 10 to the minus 4th. And that is our concentration of species at equilibrium. This, and this. I don't know if we want to circle that or whatever. So there's our part A answer. Our part B is supposed to be a pH. Now we can get that very quickly. Our pH is supposed to be the negative log concentration H3O plus, and that is the negative log of 0.013, which should give us 1.89-ish. What did I have? I had 3 sig figs there. I only had 2 there because this only had 2. So we'll go with 1.89 as the pH. And again, I kind of waved my hand at that. Our K value only had 2 sig figs. So then when I did that algebra there for the quadratic, I got 2 sig figs. And there's my 2 sig figs, which means I have 2 decimal places in my pH. So whether you like that or not, that's how it happened. And then the last step here, trying to get that percent dissociation is supposed to be x over the initial concentration times 100. Our x is 0.013 over our initial concentration, which is 0.250 times 100, and we end up with 5.2% dissociated. Or percent ionized, depending on who you're talking to. All right, so something to note. Strong electrolytes dissociate completely. That's 100% dissociation. For a 0.250 molar strong acid solution, I got a pH of 0.6. For a 0.250 molar weak acid solution, I got a pH of 1.89, and that's a pretty significant difference because instead of all of our acid turning into H3O+, we only had a small bit of our acid turning into H3O+, and most of our HF, our weak electrolyte, remained undissociated. All of it turned into this stuff for the strong, some of it turned into this stuff for the weak, and then we had quite a bit of it left. The equilibrium is reactant dominated because we got a small K value and those other words. And you don't technically need to do an ice problem for strong acids and bases. You can just look at it and say, all right, this is going to dissociate completely. Got to take the OHs into consideration. None of that's left. And you can save yourself some work. We'll do some more examples of this because there's all kinds of variations, but this is a good start.